In problems 19 through 28, graph the function f by starting with the graph of, there should be y equals x squared, and using transformation, shifting, compressing, stretching, and or reflection. Hint, if necessary, write in that form. Once I'm finished with this page, I won't have to do that anymore. But it's a necessary evil in order to try to at this stage anyway, in order to find the vertex. Nothing works without the vertex. Now, if I'm going to complete the square, here's the problem with completing the square, is that when we completed the square before, to solve a quadratic equation, what we did, if we had, let's just take it the easy way, plus 2x minus 9 equals 0, I had 0 here. So I could kick the 9 to the other side. And then I would take the coefficient of x divided by 2 and square it. That's 1. Then I would add 1 to both sides, and I'd move forward from there. So this is a perfect trinomial square. And then I would solve for x. Here's the problem. The problem is I notice that what I do not have is 0. I have, this is any y value. That makes sense. This is a range value. It's not 0. So I cannot, you know, if I had a constant there, kick the constant to the other side, complete the square, right, and do that, because this is not a number anymore. It is an infinite number of choices that can go in here. It's any y value that's in the range. That means everything has to be done on the same side. Now this is why it's kind of worth it to do this. For those of you who are going into the engineering calculus, not the business calculus, but the engineering calculus, you will do this periodically in order to put certain formulas in a form where it becomes useful. You can then there are tables and books and stuff of saying, if you have something of this form, this is what you have and this is how you use it, in the context of the application problem that you're working. But you have to have it in a particular form, and so you have to manipulate something to turn it into a form that you can actually look it up. That's one of the many things that you do. So in terms of algebra manipulation. So it's a good thing to see that indeed you can complete the square and what it's going to entail when you try to do that. And then we're going to work our way around it where you don't necessarily have to do that, at least for what we do in this class. Now what you do in calculus, you can't. Now what does this say? The first step always is, normally we say if x, the coefficient of x squared is at 1, divide it out. We can't divide it out because this is not 0. That would be f of x divided by 3. Now I have a formula. So I'm going to have to first factor the 3 out. So that f of x is 3 times x squared plus 2x. Now the coefficient of x squared is 1. I can complete the square on the x's. I take 2 divided by 1, or 2 divided by 2, and square it. That's 1. That means, whoops, I just lost my red one. That means that I'm going to add 1. But unfortunately, I did not add 1. What did I add? If I multiply through, this is 3x squared, oh, thank you, plus 6x plus 3. What did I actually add? I actually added a 3. See, that's the problem when you have to do everything on the same side. You have to account for what it really is. Now that means what I normally do is I would take 3, multiply it times what I put in. So 3 times 1 is 3. Then I remove it. So if this is a plus 3, I subtract 3. If this were a minus 3, I would add 3. Because if I remove parentheses, I need to get back to the original. The original says that's a plus 3 there. I need to remove it. So now I have that f of x is 3 times a perfect trinomial square, which is x plus 1 minus 3. Now that's in our old furry friend transformation format. So what's the transformation? What's that guy? No. Left, yeah. Because this is x minus a minus 1, right? So it's left 1. And then I'm done with the inside, and then what do I have? No. What's this?
Vertical stretch.
Vertical stretch. And what's that? Down 3. So if I were to list the transformation, it would be left 1, vertical stretch, factor of 3, and down 3. Now the beauty of the parabola is, and this guy opens how? A is positive, so how does he open? How's he open? Up, yeah. So all I need is 3 points. I need a point here and a point on either side of the vertex. And I'll choose 0, -1, and 1 for the transformation. So once I have the bowl, then you notice it goes up from the bowl, or if I choose 3 points on the guy who's going down, it goes down from the bowl. So I make sure I get the U shape in, the U part of it. Which makes it now easier to graph, because if I'm looking at the basic and put in -1, 0, 1, this is 1, 0, 1. And I'm going to go left 1, which means I'm going to subtract 1. So this is -2, -1, and 0. Vertical stretch factor of 3, multiply by 3, 3, 0, 3. And then down 3, so subtract 3, 0, -3, 0. And remember, there's our new. So -2, 0, -1, -3, 0, 0. See, notice I'm going to carefully draw my bowl, but then I know that, oop, there it goes again. It's going to continue. No, not to be able to get it. It's going to continue to go up. So quickly you can do it in 3 points, which is very nice. Now, number 2, same thing. Now I'm looking at first thing I'm going to do is I'm going to group the x's. Because that's what I'm going to complete the square on, and kick the constant to the outside. Now I'm going to do something a little on the squirrely side. I notice that this is the case. This is going to make my life easier. I notice that 4/3 can be written as, the coefficient here is 2/3 times what number? 2/3 times what is equal to 4/3? 2, yeah. So this would be 2/1. That's a trick. Because I need to factor out 2/3. And I need to figure out, how can I factor out 2/3 so life is nice? In the old days, I might have multiplied through both sides by 3. But I don't have a 0 there anymore, and that's what the problem is. But I need to get rid of the 2/3. I look at the relationship between 2/3 and 4/3 and see what would it take for me to be able to factor out 2/3. So that f of x equals, I'm going to rewrite this, 2/3 x squared plus 2/3 times 2x minus 1. Now I have a greatest common factor of 2/3. So that f of x, notice I don't have equal, 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 equal. I write f of x each time because that tells me I'm working with a formula. So that factor out of 2/3. Now here, the 2/3 is gone, so I'm left with x squared plus, here the 2/3 is gone, I'm left with 2x minus 1. That's why I wrote it as 2/3 times 2. So now I can take the 2/3, and then you can see what's going to be left over. Now I complete the square on the x's by taking 2/2 n squared, which is 1. That means I'm going to add 1, but I didn't add 1. I added 2/3 times 1. I actually added 2/3. So if I added 2/3, what am I going to have to do? Subtract 2/3. So that f of x equals 2/3 times x plus 1. And then I have 3/3 minus 2/3 is minus 5/3. So 1 is 3/3. By the way, if you're going to take calculus at all, you're going to get used to that.
Would it be x plus 1 squared?
Oh, thank you. Yes. Now from there, I can get my transformation. And I can get my vertex. My vertex is what?
1, negative.
Not 1.
Negative 5.
-1, negative 5/3. HK. See, all this stuff comes back and wraps around each other again in a different form. That's why I love college algebra. It's one of my favorites. One of my favorite courses. So if I list the transformation, I start from the inside, and what do I have? I have a minus 1, so it's left 1. And then I come out to here, and I have a 2/3, and it is a, what kind of a shrink? Vertical shrink. And this is a factor of 2/3, and I write it there because I'm going to be performing a transformation from this. And now I'm done there, and what do I have now? Down, yeah, down 5/3. Down would be the negative, or it wouldn't be wrong to say down negative 5/3. I would say same thing. So now if I want to graph this, it's x squared, that's the basic, negative 1, 0, 1, 1, 0, 1. I'm going to go left, so I'm going to add negative 1, which is going to give me a negative 2, negative 1, and 0. And then I'm going to shrink him by multiplying by 2/3, 2/3, 0, 2/3. And I'm going to go down.
You scooted over a little.
Oh, thank you. Yeah. Didn't realize that was out of bounds there. Thank you. Which is a subtract a 5/3, which is minus 2/3 minus 5/3. Oh, isn't that cute? Is minus 3/3 or? Negative 1, negative 5/3, negative 1. Ah, that's so nice. I only have one fraction I have to deal with. Whew. So, negative 2, negative 1. Negative 1, negative 1 and 2/3. Zero, negative 1. I've got a very small bowl. Now, if I wanted something better, I need to put in a couple more coordinate points. But that's good enough for us. And there he is.